Hello, good night. Tonight we are going to work through this book, Philosophy of Software Design. And long story short, the reason I'm reading this is because I've noticed I am struggling while building software with AI assisted. Like the process of the practice of AI assisted development, I am not that good right now, so I want to improve. Basically, is that. And after browsing through the internet, I watched a video of a guy named Matt Pockup. He's very experienced in AI, and he recommended basically this book. And he has AI experience. He's building a lot of stuff, and he also it's a seasoned software developer. So he in one of his keynotes, I'm going to leave the source in the video's description, but yeah, he recommended this book. And the reason is that he says that the foundations of software development start by understanding this software architecture and software design and all this. So this is not a book about coding by itself. We are not going to see, at least I don't think that we are going to see a lot of syntax, but more like a philosophy or and very to get the very big picture of how software engineering works, and specifically in this case software design. So yeah, that's all. And what you're seeing right now is my learning workspace, let's put it that way. So I'm testing this way to consume resources. Mm, the strategy is basically read the book like very streamlessly, like not stopping a lot, perhaps stopping in some moments to reason, to yeah, to reason about ideas, and yeah, just commentaries. But we're going to try to read this book uh, thoughtfully. We are not just going to go through the book and try to make a speed run. That's all the opposite I want to do. So I don't know how much is going to take this. But yeah, we're going to add statements, questions, heuristics, all these actions you can see. And later we are going to discuss this with AI. As I said, I am experimenting, so I don't know if we are going to wait for all this, like to read all the book and then send all this to the AI to process and discuss, or we are going to do it in, let's say, in chunks, in parts. So let's see how it goes. Let's improvise. So yeah, I'm going to use Cloud for this, and yeah, that's all. Let's start. So preface. People have been writing programs for electronic computers for more than 80 years, but there has been surprisingly little conversation about how to design those programs or what good programs should look like. There has been considerable discussion about software development processes, such as agile development, and about development tools such as debuggers, version control systems, and test coverage tools. There has also been extensive analysis of programming techniques such as object-oriented programming and functional programming, and of design patterns and algorithms. So all of these discussions have been valuable, but the core problem of software design is still largely untouched. David Perna's classic paper on the criteria to be used, but stay okay. Okay, so this is the first big important statement of the book. So the state of art of the art in software design has not progressed much beyond that paper. in the ensuing 45 years. So, okay, so I'm going to write down this state of art. State of art in software design has not progressed much. Yeah, and after this paper, after this after this paper, to be used in decomposing systems. Okay, it's here. Okay. Perhaps it could be useful to write here. So after, okay. So why? What happened in this paper? What presented this paper, and why the field didn't progress after this? So I guess the book is going to talk about this. The most fundamental problem in computer science is problem decomposition. How to take a complex problem and divide it up into pieces that can be solved independently. So this is a huge statement. The most fundamental, I think this is worth it to remember. The most fundamental problem in computer science is problem decomposition. So I feel comfortable putting that here. So the biggest problem in computer science is problem decomposition. It's problem decomposition. Okay. How to take a complex problem and divide it up into pieces. Okay, yeah. Problem decomposition is the central design task that programmers face every day, and yet, other than the work described here, I have not been able to identify a single class in any university where problem decomposition is a central topic. We teach for loops and object-oriented programming, but not software design. In addition, there is a huge variation in quality and productivity among programmers, but we have made little attempt to understand what makes the best programmers so much better or to teach those skills in our classes. I have talked with several people I consider to be great programmers, but most of them had difficulty articulating specific techniques that give them their advantage. Many people assume that software design skill is an innate talent that cannot be taught. However, there is quite a bit of scientific evidence that outstanding performance in many fields is related more to high quality in practice than innate ability. Yeah, this is basically growth mindset. Here we are growth mindset team. So yeah, it's the belief that you can do anything, you can achieve anything, you can learn and get any skill just by relying on practice, and put in the hours. So yeah, I totally agree with this. So software design and all this that we are going to learn, at least in my case, I'm going to start with the belief. Obviously subjective, but there is a quite a bit of scientific evidence, so it's subjective and objective at the same time, I guess. So yeah, the belief that we are capable of learning anything, just by putting the hours. Yeah, we can learn this. Just we have to focus on this, read, try to digest what we are going to learn, and practice, practice, and more practice. So, yeah, for many years, these issues have perplexed and frustrated me. I have wondered where software design can be taught, and I don't know how to pronounce this word, and I have hypoth. Now let's see. My English is failing in this very moment, but growth mindset, guys. Hypothesize, hypothesize, and I have hypothesize, yeah, hypothesize that design skill is what separates great programmers from average ones. Okay, so the hypothesis of the author is that design skill is paramount. If we want to be great software engineers, great programmers, we need to learn this. We need to learn software design. So this is another statement that I find it might be useful or perhaps motivating, perhaps in a day that we forget how important is this topic. I find it useful to have it here. So software design is a skill that differentiates great programmers from average ones. I finally decided that the only way to answer these questions was to attempt to teach a course on software design. Yeah, the best way to learn something is by teaching. In some way, that is the reason that I'm recording this, because I know nothing, barely. I know a couple of words, but no more than that. And I want to learn this properly, so I thought, okay, I'm going to record myself while learning this and while trying to somehow explaining what I am learning. So I I kind of agree. I agree with this approach. So yeah, was the attempt. The result is the CS 190 at Stanford University. In this class, I put forth a set of principles of software design. Students then work through a series of projects to assimilate. Okay, the class is taught in a fashion similar to a traditional English writing class. In an English class, students use an iterative process where they write a draft, get feedback, and then rewrite to make improvements. In CS 190, students develop a substantial piece of software from scratch. Then we then go through extensive code reviews to identify design problems, and students revise their projects to fix the problems. This allows students to see how their code can be improved by applying design principles. I have now taught the software design class 3 times, and this book is based on the design principles that emerge from the class. Good. So these teachings are based from a hands-on approach. So I like it. I like it. We are basing all this in real case scenarios, we could say. The principles are fairly high level and border on the philosophical, define errors out of existence, so it is hard for students to understand the ideas in the abstract. Students learn best by writing code, making mistakes, and then seeing how their mistakes and the subsequent fixes relate to the principles. Yeah, this is about feedback loops. In order to improve a process, a system, whatever, we need to increase feedback loops. We need to measure performance, and we need to find a way to get information about performance often. Like, we cannot improve a system if we cannot measure or if we are not tracking. how the system is performing. So yeah, it's that applied to learning. At this point, you might well be wondering, what makes me think I know all the answers about software design? Oh, okay. Technical stop. Okay, problem solved. So, to be honest, I don't. There were no classes on software design when I learned to program, and I've never had a mentor to teach me design principles. At the time I learned to program, code reviews were virtually non existent. Okay, my ideas about software design come from personal experience writing and reading code. Over my career, I have written about 250,000 lines of code in a variety of languages. I've worked on teams that created three operating systems from scratch, multiple file and storage systems. Okay, this guy, it's a great programmer with a lot of experience, professional experience. After that, he became a teacher. So yeah, he has he has something to say. So I don't expect this book to be the final word on software design. I am sure that are there are valuable. Always, I don't know if I am pronouncing this word correctly. Valuable, valuable. Okay, that's a difference. There are valuable techniques that I've missed, and some of my suggestions may turn out to be bad ideas in the long run. However, I hope that the book will start a conversation about software design. Okay, this book is an opinion piece, so some readers will disagree with some of my suggestions. I like this honesty. I will I wouldn't trust too much a guy that claims that he has the absolute and last truth. Uh, yeah, no, you have to acknowledge ignorance. So this is a green flag, if you wish. If you do disagree, try to understand why. Okay. Okay. Yeah, he's interested on getting feedback. Yeah, and okay, he's mentioned people that were important in the development of this book. We can skip that with all due respect, of course. So, chapter 1, Introduction. It's all about complexity. Writing computer software is one of the purest creative activities in the history of the human race. It's a creative activity. Writing computer software is creative activity. This is okay. Another statement. Writing computer programs programs is a creative activity. Programmers aren't bound by practical limitations such as the laws of physics. We can create exciting virtual worlds with behaviors that could never exist in the real world. Programming doesn't require great physical skill or coordination like ballet or basketball. All programming requires is a creative mind and the ability to organize your thoughts. If you can visualize a system, you can probably implement it in a computer program. This means that the greatest limitation in writing software is our ability to understand the systems we are creating. Okay. As a program evolves and acquires more features, it becomes complicated with subtle dependencies between its components. Over time, complexity accumulates, and it becomes harder and harder for programmers to keep all of the relevant factors in their minds as they modify the system. This slows down development and leads to bugs, which slow development even more and add to its cost. Complexity increases inevitably over the life of any program. The larger the program and the more people that work on it, the more difficult it is to manage complexity. Okay. Good development tools can help us to deal with complexity, and many great tools have been created over the last several decades. But there's a limit to what we can do with tools alone. If we want to make it easier to write software so that we can build more powerful systems more cheaply, yeah, this is what I'm trying to achieve for the AI models that I am trying to use to write software. I want for them to that writing software it's easy, easy to understand, to navigate, to create, to modify. And most of my mistakes are fundamented on this. I gave AI a dirty code base, a very complex code base. I think that that is the start of the problem. Okay, so if we want to make it easier to write software so that we can build more powerful systems more cheaply, we must find ways to make software simpler. Yeah, I agree. Complexity will still increase over time. Yeah, so this is like entropy, I guess. It's unavoidable that complexity increases. So I guess that good design is about creating strategies to avoid this, or not to avoid, to minimize the how much increases complexity. So in spite of our best efforts, but simpler designs allow us to build larger and more powerful systems before complexity becomes overwhelming. Yeah, there are two general approaches to fighting complexity, both of which will be discussed in this book. The first approach is to eliminate complexity by making code simpler and more obvious. For example, complexity can be reduced by eliminating special cases or using identifiers in a consistent fashion. The second approach to complexity is to encapsulate it so that programmers can work on a system without being exposed to all of its complexity at once. Okay, encapsulate complexity. That is interesting. So yeah, see, if complexity is unavoidable, why not encapsulating it and exposing just what a programmer, or in this case, just what the AI needs. We don't need to expose every detail of a system through its interface. I think that this is where it's going. This approach is called modular design. This is important, I guess. So, wait. So, modular design is an approach. It's a way approach, yeah. It's it's an approach to fight complexity. It consists in encapsulating encapsulating it and exposing only what what is needed, It was and expose and exposing. I don't know how to reframe this without being exposed to all of its complexity at once, and exposing only what is essential. I will say, and exposing strategically, and exposing it strategically. I will. I like this way of put it. So okay, because software is so malleable, software design is a continuous process that spans the entire life cycle of a software system. This makes software design different from the design of physical systems such as buildings, chips, or bridges. However, software design has not always been viewed this way. For much of the history of programming, design was concentrated at the beginning of a project, as it is in other engineering disciplines. The extreme of this approach is called the waterfall model, in which a project is divided into discrete phases such as requirements, definition, design, coding, testing, and maintenance. So in the waterfall model, each phase completes before the next phase starts. In many cases, different people are responsible for each phase. The entire system is designed at once during the design phase. The design is frozen at the end of this phase, and the role of the subsequent phases is to flesh out and implement that design. Well, I don't know this phrasal verb, flesh out. To add more information or details to a plan argument. Okay, it's like develop. The design is frozen at the end of this phase and the role. Okay, so the waterfall model is an approach of design. I like, wait, software design is a continuous process spanning through spanning the entire life cycle of software of a software system. Yeah, of a software system. And the waterfall approach consists on or in, I don't know, perhaps they are synonyms. The waterfall approach consists in. So yeah, I'm going to try to remember this. This is good for learning, not just always relying on just going to the source and like copy and paste or transcribe. It's not a good learning strategy. It's good to force yourself to remember. So, what is the waterfall approach? Waterfall approach consists in implementing like all the uh, phases of a project or of a system sequentially. Sequentially. This contradicts, so this highly contradicts with this statement. Software design is a continuous process. So if software design is a continuous process, if that is true, the waterfall approach is a bad design approach. Why? Because in the waterfall approach, design is going to be the first phase, and we do that, and we call it a day, at least with the design. So it's not a continuous process in the waterfall approach. This contradicts, e- perhaps this is redundant. Therefore, this approach is a bad design, produces bad designs. I don't know if I don't like a lot using these words like bad, good. It's very, it's like very general. They are very general words that can mean anything for anyone. So it's better to use more precise words. So therefore, this approach produces more complexity. Like it's the logic. If good designs, if good design minimizes complexity, then bad design produces more complexity. If the waterfall approach it's a bad design approach, then it produces more complexity. Easy, easy and simple, isn't it? So where we were at? Okay, testing. Okay, unfortunately, the waterfall model rarely works well for software. Oh, big surprise. Software systems are intrinsically more complex than physical systems. It isn't possible to visualize the design for a large software system well enough to understand all of its implications before building anything. Yeah, I guess it's. I don't know if this is a correct statement, but I don't know where I read that supposedly Albert Einstein said something like the only difference between the theory and practice is that in theory they are the same, but in practice they are not. So I think it's like this. It's related with this. So as a result, the initial design will have many problems. The problems do not become apparent until implementation is well underway. And in the waterfall approach, we in that moment it's too late to change the design. However, the waterfall model is not structured to accommodate major design changes at this point. Thus, developers try to patch around the problems without changing the overall design. This results in an explosion of complexity. Yeah, I've heard this as the famous or the infamous technical debt. So, technical debt increases complexity, I guess. Because of these issues, most software development projects they use an incremental approach such as agile development. So I don't know a lot right now about this. I kind of know that it consists in splitting, dividing a project in sprints, and that's all I know about agile development. So for now, we are going to put it here. So what is agile development? So later, I'm going to dedicate uh, a study session to learn about this. So hopefully, by the end of the process of the processing of all these statement questions and all the stuff that we are going to write down, eventually I'm going to understand this is unavoidable, I guess. If you understand all the words used and understand how they relate to each other, it's unavoidable that you understand anything, I guess. So yeah, let's leave it here, this question. And I don't think that it's worth studying that right now. Perhaps it's out of scope because the incremental approach, yeah, incremental approach in each sprint, you adapt to how the development process is going on. So for now, let's leave it here. In which the initial design focuses on a small subset of the overall functionality. This subset is designed and implemented and then evaluated. Problems with the original design are discovered and corrected. Then a few more features are designed, implemented, and evaluated. Each iteration exposes problems with the existing design, which are fixed before the next set of features is which are fixed before the next. Okay. By spreading out this design in this way, problems with the initial design can be fixed while the system is still small. Later features benefit from experience gained during the implementation of early features, so they have fewer problems. The incremental approach works for software because software is malleable. I don't know if I'm pronouncing this correctly. Let's see, malleable, malleable, malleable enough to allow significant design changes partway through implementation. In contrast, major design changes are much more challenging for physical systems. For example, it would not be practical to change the number of towers supporting a bridge in the middle of construction. Yeah, this is one of the big differentiators. It's kind of obvious saying that, but I think it's important for any software engineer to be conscious of this. And it's the property of software systems that they are very, very malleable in contrast to physical systems. So it's like obvious stating this, but for me, it was not obvious uh, in the very beginnings of my career. I am still in the beginnings, but when I was more beginner, this was not obvious. So try to understand this. I think it's important. Software systems are characterized by being highly malleable. Okay, let's continue. Incremental development means that software design is never done. Design happens continuously over the life of a system. Developers should always be thinking about design issues. Incremental development also means continuous redesign. The initial design for a system of components is almost never the best one. Experience inevitably shows better ways to do things. As initial design for a system. I like to write a settled custom note about this. I'm going to. This is. Let's create here and a settled custom. If you don't know what is this settled custom, it's a study, a strategy, methodology approach that consists basically in forcing yourself to learn by writing. By writing, meaning essays, and yeah, it's basically doing that. So later, I'm going to take this statement and I'm going to write about it. Better, it will be better to do this when I finish the book or when I am more advanced. So I can develop, I can flesh out the idea, the idea of this statement, and how I integrate this learning methodology is that after I write and publish a settled custom node, this is a material for uploading, for posting in social media. So yeah, I will have after this a better on two things, a better understanding on this statement, on this topic, and two, I will have a ready or almost ready polished post for social media. So it's a win-win situation. So let's leave it there and let's continue. As a software developer, you should always be on the lookout for opportunities to improve the design of a system you are working out. So perhaps this can be considered a heuristic. Like it's a heuristic, I see it as simple rule or a simple action that it's part of a bigger protocol. So I want to remember this whenever I am designing a software component or software system, that I need to be on the lookout for opportunities to improve the design. So I think this is a heuristic. Yeah, I should always be on the lookout. It's for opportunities to improve the design the design of a system. So what's the idea? I'm going to try to like sort of get these yeah, heuristics or rules of thumb, and then at the end, during the AI processing stage of this node, we're going to try to create a protocol, like something that encompasses all these heuristics in one single protocol or one standard, one workflow, whatever. So I can extract, I can obtain a practical practical knowledge about this book. So this is the way that I I use or and I am hoping that it works for this this problem that when you study theory and you are only studying and learning theory, that that is not bad by itself, studying theory, but when you don't balance it with a hand-on experience, with hands-on skills, you are missing the you are missing something, like the Albert Einstein approach. Theory and practice are different. So this about the statements, questions, insights are more about the theoretical side of this, but heuristics and protocol sections are going to be to try to come up with a practical practical tool, practical workflow. So that's the idea. So I should always be on the lookout for opportunities to improve the design of a system. This is a good thing to remember. And you should plan on spending some fraction of your time on design improvements. I think this is okay. Yeah, this we don't need to add that. If software developers should always be thinking about design issues and reducing complexity is the most important element. Wait. If software developers should if software developers should always be thinking about design issues and reducing complexity is the most important element of a software system, then software developers should always be thinking about complexity. So yeah, complexity, complexity, complexity. This is a very important word to understand and to keep in our minds when thinking about software design. This book is about how to use complexity to guide the design of software throughout its lifetime. Okay, complexity is important. This book has two overall goals. The first is to describe the nature of software complexity. What does complexity mean? Okay, what does complexity mean? Why does it matter? So we are going to leave these questions here, but these questions are going to be answered in a moment. What is complexity? What is complexity? Okay, the book is going to explain to us the nature of complexity, what is, why does it matter, and how we can recognize it. And it's going to present to us uh, practical techniques. So again, very good theory, hands-on approach. Very good. I agree totally with this. Unfortunately, there isn't a simple recipe. I think this is pronounced recipe, but I don't know. Recipe? Yes, yes, sir. It isn't a simple recipe that will guarantee great software designs. Instead, we will present a collection of higher level concepts that border on the philosophical, such as classes should be deep. These concepts may not immediately identify the best design, but you can use them to compare design alternatives and guide your exploration of the design space. How to use this book? Many of the design principles described here are somewhat abstract, so they may be hard to appreciate without looking at actual code. The best way to use this book is in conjunction with code reviews when you read other people's code. So we have a lot of code, a lot of code to read thanks to AI. So perfect. Think about whether it conforms to the concept discussed here. Okay, it's easier to design problems in someone else's code than your own. This is a topic by itself. It is easier to see design problems in someone else's code than your own. So it's it's better to learn. This is a question that I have totally out of scope. Like, is it possible to become a great code reviewer without doing manual programming? I don't know. I I would like that this is true because I want to be great at reading. Like, I want to be the best at reading pull requests. Like, I see the pull request, I see the files that were changed, and the skill to be able to identify the components that were changed, how the changes change the relationships of the system. That is a great skill, especially nowadays in AI's era. So I hope that you can be great at reading code without having to write it or to go through a previous season of coding manually. So I hope. Let's see. But yeah, let's go back to the book. So you can use red flags described here to identify problems and suggest improvements. Reviewing code will also expose you to new design approaches and programming techniques. One of the best ways to improve your design skills is to learn to recognize red flags. Okay, so I will point out over the course of this book, I will point out red flags that suggest problems related to major design issues. The most important ones are summarized at the back of the book. Okay, you can then use these when you are coding. When you see a red flag, stop and look for an alternate design that eliminates the problem. When you first try this approach, you may have to try several design alternatives before you find one that eliminates the red flag. Don't give up easily. The more alternatives you try before fixing the problem, the more you will learn. Over time, you will find that your code has fewer and fewer red flags. Okay, when applying the ideas from this book, it's important to use moderation and discretion. Every rule has its exceptions, and every principle has its limits. Yeah, this is not like the definitive laws of design. This is an approach, and it can be wrong. So we need to be sensible when choosing what techniques of design to follow. It all depends in the context of the situation. If you take any design idea to its extreme, you will probably end up in a bad place. Okay, beautiful designs reflect a balance between competing ideas and approaches. Okay, several chapters have sections titled Taking It Too Far. It's interesting. Almost all of the examples in this book are in Java or in C++, and much of the discussion is in terms of designing classes in an object-oriented language. However, the ideas apply in other domains as well. Yeah, I think design is, in general, is a topic about engineering. So in this case, we are going to see how design works or should work in software engineering. But I guess this, hmm, wait, yeah, the design phase is in all engineering fields, but it's not followed with the same approach because of malleability, because of how malleable is a system. So the design approach cannot be iterative, I guess, in civil engineering, like building bridges and so. So yeah, let's continue this. We, this that question is going to be answered through experience, not by theorizing here, I guess. However, the ideas apply in other domains as well. Almost all the ideas related to method. Okay. With this background, let's discuss in more detail what causes complexity and how to make software systems simpler. Okay, chapter 2. The nature of complexity. This book is about how to design software systems to minimize their complexity. The first step is to understand the enemy. Exactly what is complexity? How can you tell if a system is unnecessarily complex? What causes a system to become complex? This chapter will address those questions at a high level. Subsequent chapters will show you how to recognize complexity at a lower level in terms of specific structural features. The ability to recognize complexity is a crucial design skill. Another important statement, but we have something similar. Let's see, software design is a skill, okay. No. So in the skill set of software design, We could state we could state it like that. In the skill set of software design, the ability to recognize complexity, recognizing complexity is a paramount skill, sub-skill, skill, whatever. Recognizing complexity is a paramount skill. Recognizing complexity. So, this is a horrible typo. What is complexity? How to recognize it? Let's see. It allows you to identify problems before you invest a lot of effort in them, and it allows you to make good choices among alternatives. It is easier to tell whether a design is simple than it is to create a simple design. It is easier to tell whether a design is simple than it is to create. Okay. But once you can recognize that a system is too complicated, you can use that ability to guide your design philosophy towards simplicity. If a design appears complicated, try a different approach and see if that is simpler. Over time, you will notice that certain techniques tend to result in simpler designs, while others correlate with complexity. This will allow you to produce simpler designs more quickly. Okay, this is about heuristics. I believe we will find it out on the way. This chapter also lays out some basic assumptions that provide a foundation for the rest of the book. Later chapters take the material of this chapter as given and use it to justify a variety of refinements and conclusions. Okay, so this is a foundational chapter, important to be attentive. Complexity defined. For the purposes of this book, I define complexity in a practical way. Complexity is anything related to the structure of a software system that makes it hard to understand and modify the system. To the structure of a software system. So the structure is about what components does the system have and the relationships, like, yeah, structure is obviously, it has nothing to do with behavior. So complexity is not about behavior, it's about structure of a system. So a system becomes more complex by modifying its structure. It makes sense. So two systems with same behavior, one can be totally and utterly complex, and the other one can be simpler to operate with. Okay, let me think about this definition. Perhaps I want to transcribe it. Complexity is related to structure. So I could restate it as any anything that makes no complexity is related to structure. Complexity is about structure rather than behavior. The the harder is to understand or and work and modify a system, the harder it is. The more complex, we say that system is. I like this statement more. Okay. Complexity can take many forms. For example, it might be hard to understand how a piece of code works. It might take a lot of effort to implement a small improvement, or it might not be clear which parts of the system must be modified to make the improvement. It might be difficult to fix one book without introducing another. Yeah, this is a hell I can imagine. Even tiny fixes can produce, let's say they have a huge blast radius. This is one of the biggest consequences of complexity, I believe. You can also think of complexity in terms of cost and benefit. In a complex system, it takes a lot of work to implement even small improvements. Yeah, I would like later to write a settled custom note about this. Cost and benefit in a complex system. Yeah, it's I want to write something about this propriety, this relationship. Where is the here? It's like what is this here? So complexity takes away takes away the very advantage of software systems. That is, which is malleability. Malleability. Yeah. Mm, now let's say complexity makes. Okay, we will define a general title. I will later polish this. Complexity makes harder to modify a system, effectively taking away how malleable it is. Okay, complexity is what a developer experiences at a particular point in time when trying to achieve a particular goal. It doesn't necessarily relate to the overall size or functionality of the system. People often use the word complex to describe large systems with sophisticated features. But if such a system is easy to work on, then, for the purposes of this book, it is not complex. Of course, almost all large and sophisticated software systems are in fact hard to work on, so they also meet my definition of complexity. But this need not necessarily be the case. It is also possible for a small and unsophisticated system to be quite complex. Complexity is determined by the activities that are most common. If a system has a few parts that are very complicated, but those parts are almost never need to be touched, then they don't have much impact on the overall complexity of the system. To characterize this in a crude mathematical way, The overall complexity of a system is determined by the complexity of each part, weigh, weighted, weighted by the fraction of time developers spend working on that part. Isolating complexity in a place where it will never be seen is almost as good as eliminating the complexity entirely. This might be a heuristic, I believe. I I feel it might be a part of a protocol in the future. So let's write it down. So let's go to heuristics. So in yeah, I forgot to mention, but the let's say the long term goal of this nodes is basically to create based on this after processing and discussing and all that. After doing that, the idea is to create a skill of software design or software architecture, whatever we decide at that moment. But yeah, that is the long term goal. So it's to produce a skill like polished by me, filter, curated, if you wish. A skill that I understand, or I should understand. Hopefully, I will. So I will be more control when I use this skill in the future. When I'm dealing with a complex code base, then the idea is basically to yeah in this skill to specify the protocols, the reminders, anything that an AI should understand or should remember about this. But yeah, that is for later. Just leave it in for the record. Okay. Oh, the heuristics. Yeah, isolating complexity in a place where it will never be seen. In a place where it will never be seen is almost as good as eliminating complexity. Complexity is more apparent to readers than writers. I hope this is a point in favor of this idea of you can learn how to read quickly and effectively code without having to write it before or to have this muscular memory. Okay, let's continue. Complexity is more apparent to readers and writers if you write a piece of code and it seems simple to you, but other people think it is complex, then it is complex. Simple. When you find yourself in situations like this, is where probing. I don't know this word, but let's see. But I think it's like testing. I can get the context. I guess it's word probing. Let's see. Intended to discover the truth. Let's look for the verb to ask questions in order to find out the secret. Yeah, kind of. Touch. Okay. It's worth probing the other developers to find out why the code seems complex to them. There are probably some interesting lessons to learn from the disconnect between your opinion and theirs. Yeah, biases are pretty dangerous. Your job as a developer is not just to create code that you can work with easily, but to create code that others can also work with easily. And this includes AI agents, of course. Yeah, wait. From the very beginning that I learned the basics of programming, I heard a lot this statement. You have to create stuff that is easy to others to work with. But we need to apply that mindset that's also for AI agents, not only for humans, because nowadays a lot of code is written by AI. So that's the question. What makes a code base? That's a good question. Yeah, probably we will answer it during the reading of this book. So, what makes a code base easy to navigate and modify for an AI agent? Let's simplify this. What makes a code base easy to work with? Okay, symptoms of complexity. Complexity manifests itself in three general ways, which are described in the paragraphs below. Each of these manifestations makes it harder to carry out development tasks. Change amplification. Symptoms of complexity. The first symptom of complexity is that a seemingly simple change requires code modifications in many different places. Okay, I guess this is a sort of red flag as well. Change amplification. I like that way to summarize the idea. Change amplification. So symptoms was written like that. Symptoms, yeah. Symptoms of complexity. Let's put this in bold because it is important. So change amplification. The first symptom of complexity is that a seemingly simple change requires code modifications in many different places. Change amplification. For example, consider a website containing several pages, each of which displays a banner with a background color. In many early websites, the color was specified explicitly on each page, as shown in figure. Okay. Each page in a website displays a colored banner. Okay. In A, the background color for the banner is specified explicitly in each page. In B, a shared variable holds a background color and each page references that variable. Okay. Okay, I got the example in order to change. Yeah. Cognitive load. The second symptom of complexity is cognitive load, which refers to how much a developer needs to know in order to complete a task. Cognitive load. A higher cognitive load means that developers have to spend more time learning the required information and there is a greater risk of bugs because they have missed something important. Okay, allocates memory, returns a pointer to that memory, and assumes that the color will free. Okay, I don't know a lot about. see, but I can remember this. You have to be very explicit with how memory is managed. So yeah, if you create a variable or you're going to use memory, you have to explicitly free it up. So returns assumes that the yeah, so like the function is not, or perhaps the documentation, the function is not doing this automatically when it should be, because of this complexity. Because now the caller needs to remember this every time the function is called. So this increases the probability of failure. I You can remember do that in one, two, three, but as the number starts to increase, the number of times you use that function, it's simple mathematics, statistics. You are going to forget that in in a certain moment. Is unavoidable. So this adds to the cognitive load of developers using the function. If a developer fails to see the memory, there will be a memory leak. If the system can be restructured so that the caller doesn't need to worry about freeing the memory, it will reduce the cognitive load. Yeah, system designers sometimes assume that complexity can be measured by lines of code. They assume that if one implementation is shorter than another, then it must be simpler. However, this view ignores the cost associated with cognitive load. I have seen frameworks that allowed applications to be written with only a few lines of code, but it was extremely difficult to figure out what those lines were. Sometimes an approach that requires more lines of code is actually simpler because it reduces cognitive load. Yeah, so that it's the word an interplay. Let's see, interplay. The way, yes, exactly that word. So there is an interplay between lines of code. Now I don't know if it is an interplay. Wait, let me think about this. I mean, there is no a rule of thumb that tells you that the more the more lines of code you have, the more complex a system is. It could be actually all the opposite. It makes sense here. I have seen frameworks that allowed applications to be written with only a few lines of code. So yeah, now this about cognitive load makes more sense because yeah, you have a few lines of code, but let's take the example of this function about C that they're in they're in free memory automatically. So let's suppose we have stuff like that in these few lines of code. Those functions are doing stuff that we don't know. Perhaps they are not leaving anything like memory memory leaks or something like that. But the cognitive load is that they are doing a lot of stuff in very few lines. So trying to compress all that functionality in such a small tiny interface, maybe that is what is referring the Hauser. Because if you try to compress a lot of functionality, you need to abstract, you need to design an interface, an API to interact with all this functionality. And I guess that it might be pretty difficult to try to squeeze the more you can a behemoth of functionality. It, it might be in that train of thought, could be, but yeah, the conclusion is that we should not um, measure how complex a system is by the lines of code. It might it might be misleading. It could be worth to perhaps this is a heuristics. Nah, let's leave it like that. Okay, on now unknowns. The third symptom of complexity is that it is not obvious which pieces of code must be modified to complete a task, or what information a developer must have to carry out the task successfully. Yeah, unknowns. This is kind of related with cognitive load because if you don't know something, if you don't know that there are unknowns, wait, unknown unknowns. This is not what obvious code. Yeah, this is like cognitive overload was cognitive load. Yeah, it's related. It is not obvious which pieces of code must be modified to complete a task, or what information a developer must have to carry out the task successfully. Are the worst. Okay. An unknown means that there is something you need to know, but there is no way for you to find out what it is, or even whether there is an issue. Yeah, it's like problems that are sneaking, are waiting there in the darkness, waiting for a user or a developer touching something. And yeah, the blast radius is it could be pretty big. So yeah, but it's pretty related with cognitive load. You won't find out about it until books appear after you make a change. Change amplification. Yeah, and imagine that all that meets together. You have change amplification and you have a book, an unknown, and then you touch something innocently, and the blast radius, the change amplification makes the problem to explode. Yeah, it's pretty relatable. I think that's the word for that. Relatable, relatable. Yes, exactly. Let's um on notes. Okay, one of the most important goals of good design is for a system to be obvious. This is the opposite of high cognitive load and unknown unknowns. In an obvious system, a developer can quickly understand how the existing code works and what is required to make a change. An obvious system is one where a developer can make a quick guess about what to do without thinking very hard, and yet be confident that the guess is correct. Okay, this is a statement. One of the most Okay, causes of complexity. So now that you know the high level symptoms of complexity and why complexity makes software development difficult, the next step is to understand what causes complexity so that we can design systems to avoid problems. So that we can design systems to avoid the problems. Complexity is caused by two things: dependencies and obscurity. This is another big statement, very important to remember. Complexity is caused by two things: dependencies, dependencies, and obscurity. So what does this mean? For the purposes of this book, a dependency exists when a given piece of code cannot be understood and modified in isolation. The code relates in some way to other code, and the other code must be considered and or modified if the given code is changed. Okay, so the more components in a system depend on others, the more complex is the system. But a system is characterized by components and relationships. So, this sounds like is the word for this a conundrum? I don't know. It just came to my head. Co- Conundrum. I don't know. I don't even know how you write that. Okay, immersive method is working for English. It seems. So, for the purposes of this book, dependency exists when a given piece of code cannot be understood. Yeah, but dependencies are inherent of a system. Okay, let's. The signature of a method creates a dependency between the implementation of that method and the code that invokes it. Okay, I get that. Yeah, if the actual implementation changes, you need to change the parameters, but this is not necessarily true always. But yeah, I think that for the example, I understand what does this mean. Like there is a potential dependency between the signature of a method and the behavior, because if in the implementation of this method you change something related with the signature, the parameter the method receives or something, you have that dependency. You need to be aligned. You need to align the signature of the method with the change in the implementation. So okay, it's in, yeah, it's a dependency, but how works this with systems? Like, let's see how the book answers this. Dependencies are a fundamental part of software and can be completely eliminated. Okay. In fact, we intentionally introduce dependencies as part of the software design process. So this is another unavoidable thing: dependencies. As complexity, dependencies are, but this is interesting because complexity is caused by two things, and one of these. one of these is unavoidable. So, good design is more of a preemptive preemptive skill than a skill that you apply on the no. It's also a continuous process. Hmm. Yeah, I believe I could. This section is for, at least for now. I think about this insights section. Like, we get the statements. I mean, if you remember what I mentioned about the settled custom method, that is about writing stuff in your own words. So that's kind of a the spirit in this. The statements obviously are most like extracted and restated minimally from the book. So this is not in the settled custom math methodology. But I like to taking this and taking uh, more paragraphs in the book to extract insight that are like statements but written in my own words. Let's see how this goes, how this goes, and how this goes. And I'd like to create an insight about this, or perhaps a subtle custom note by itself. Dependencies are a fundamental part of software. Let's write a subtle custom. So, no, I don't feel so complexity. No. It's one subtle custom for this software design is a strategic endeavor. It prevents and hot fixes. It's about by designing strategies to minimize the unavoidable rise in dependencies and thus complexity. Software by using strategies to minimize the unavoidable rise in dependencies and thus complexity. Software design um, software design is a lot about preemptive. I don't know. This is the correct word. Preemptive. Preemptive. Yes. It's is a lot about preemptiveness. No, preemptive. prevention. Yeah, let's leave it like that, tentatively. Allowed. Wait, we are missing one word here. It's all about preemptive actions. Actions. In fact, we intentionally, okay, yes, yes. The old website with the background specified. Yeah, I got it. It's simple. No, let's do it thoughtfully, as we said. Consider the website sample. In the old website with the button specified separately on each page, all of the web pages were dependent on each other. The new website fits this problem by specifying the background color in a central place and providing an API that individual pages use to retrieve that color when they are rendered. The new website eliminated the dependency between the pages, but it created a new dependency around the API for retrieve. Right? I always have problem pronouncing this word. A new dependency around the API for re- retrieve, like retrieving or retrieve. Yeah, it's retrieving. Yeah, I don't know. I think sometimes it's retrieving. It's it's the artistic side of English pronunciation. You have to. There is no like general rules. Some words have their own pronunciation. Okay, let's continue. But it created a new dependency around the API for retrieving. I said it right. Retrieving. Yeah, retrieving the background color. Fortunately, the new dependency is more obvious. It is clear. Yeah. I got it. Compiler help to manage API dependencies. Yeah. The second cause of complexity is obscurity. Obscurity occurs when important information is not obvious. A simple example is a variable name. Okay, variable names, documentation for a variable that might not specify its units. Inconsistency is also a major contributor to obscurity. If the same variable name is used for two different purposes, it won't be obvious to developers which of these purposes a particular variable serves. In many cases, obscurity comes about because of inadequate documentation. Yeah, you have to document properly, especially for AI. However, obscurity is also a design issue. If a system has a clean and obvious design, then it will need less documentation. This is an interesting statement. It might be a heuristic. I don't know. For now, if a system has a obvious, clean, and obvious design, then it needs less documentation. The need for extensive documentation is often a red flag that the design isn't quite right. Red flag. So let's replace this red flag. A system needing a lot of documentation. But yeah, how much is a lot? It's subjective, but yeah, we will later try to define this more exactly, more precisely. But let's continue for now. The need for extensive documentation is often a red flag. Okay, the best way to reduce obscurity is by simplifying the system design. Together, dependencies and obscurity account for the three manifestations of complexity. So, let's try to apply to remember this. This is a good way to exercise learning, understanding, and recall in general. So, the three manifestations of complexity described in section 2.2. So, what were those? Try to think of those by yourself, but if I'm not wrong, they were cognitive load, change amplification in unknown unknowns. I think those were, yes, symptoms. Yeah, yes, sir. So we are good. We are remembering for now. Dependencies lead to change amplification and a high cognitive load. Security creates, okay, okay. Complexity is incremental. Complexity isn't caused by a single catastrophic error. It accumulates in lots of small chunks. So I think this is the worst part of complexity. That it's like habits in life. It's the small, the day by day, the little additions you do or you make. So it's dangerous because yeah, it will accumulate silently one day at a time. Then you have 1 day, 2 days, 3 days adding changes with bad design that by themselves are not bad, are not too catastrophic. It's the word. But yeah, if you continue that habit, imagine looking back at 1 month, the code base will be way more complex than before. And add to that, if there are several people working on the system. So yeah, I think I should write down this. Complexity is incremental. Title it's a good summary. Increment. Yeah. The incremental nature of complexity makes it hard to control. It's easy to convince yourself that a little bit of complexity introduced by your current change is not big deal. However, if every developer takes this approach for every change, complexity accumulates rapidly. Once complexity has accumulated, it is hard to eliminate, since fixing a single dependency or obscurity will not, by itself, make a big difference. In order to slow the growth of complexity, you must adopt a zero tolerance philosophy, as discussed in Chapter 3. Okay. Conclusion. Complexity comes from an accumulation of dependencies and obscurities. As complexity increases, it leads to change amplification and a high cognitive load and unknown unknowns. As a result, it takes more code modifications to implement each new feature. In addition, developers spend more time acquiring enough information to make the change safely, and in the worst case, they can even find all the information they need. The bottom line is that complexity makes it difficult and risky to modify an existing code base. This was a good chapter, and one of the most, I think, important insights, takeaways of this lesson is that by having a system with bad design, we are reducing the time that we will actually be improving the system, if you wish. Because in a complex code base, you will spend a lot of time just trying to understand what is happening. Where are the variables, the relationships, how each component touch touches each other, and the blast radius. If you touch one, what are the potential other components that might change? So this is software engineering, after all, in some way. But it's like we don't have to go through this situation, right? With good design, we can avoid all this and spend more time taking important decisions like more architecture, I guess, like caring about feedback loops in the system and improving functionality. But instead, with bad design, we spend a lot of time just like firefighting the books that are coming up. So yeah, good designing takes even more importance with this conclusion. Okay, chapter 3. Working code isn't enough. Strategic versus tactical programming. One of the most important elements of good software design is the mindset you adopt when you approach a programming task. Many organizations encourage a tactical mindset focused on getting features working as quickly as possible. However, if you want a good design, you must take a more strategic approach where you invest time to produce clean designs and fix problems. This chapter discusses why the strategic approach produces better designs and is actually cheaper than the tactical approach over the long run. Okay, so tactical programming. Most programmers approach software development with a mindset I call tactical programming. In the tactical approach, your main focus is to get something working, such as a new feature or a bug fix. At first glance, this seems totally reasonable. What could be more important than writing code that works? However, tactical programming makes it nearly impossible to produce a good system design. Yeah, because you're thinking in the short run. Yes, yes. The problem with tactical programming is that it is short-sighted. If you're programming tactically, you're trying to finish a task as quickly as possible. Perhaps you have a hard deadline. As a result, planning for the future isn't a priority. You don't spend much time looking for the best design. You just want to get something working soon. Yeah, and this is not bad by itself. I mean, there are moments in our daily lives or whatever in which we will need to take decisions like this, either in our lives, in our job. Like sometimes we need to think and act in the short term. But it's like they said here, yeah, you must adopt a zero tolerance. Yeah, it's like almost zero tolerance, but there will be moments unavoidably in which you are going to have to do tactical programming. But as long as we can avoid that, we are going to do it. Oh, okay. Or let's see what the author says about this early conclusion of mine. So, however, the problem with tactical, okay, You tell yourself that it's okay. Yeah, I told myself that. To add a bit of complexity or introduce a small clut clutchel. Don't know that word. Clutchel, clutch, a clutch. A solution to a problem that has been quickly and badly put together. What? A solution to a problem that has been quickly. Okay, it's a exotic word. A small clutch. If that allows the current task to be completed more quickly. This is how systems become complicated. As discussed in the previous chapter, complexity is incremental. It is not one particular thing that makes a system complicated, but the accumulation of dozens or hundreds of small things. Yeah. If you program tactically, each programming task will contribute a few of these complexities. Each of them probably seems like a reasonable compromise in order to finish the current task quickly. However, the complexities accumulate rapidly, especially if everyone is programming tactically. Before long, some of the complexities will start causing problems, and you will begin to wish you hadn't taken those early shortcuts. But you will tell yourself that it's more important to get the next feature working than to go back and refactor existing code. Refactoring might help out in the long run, but it will definitively slow down the current task. So you look for quick patches to work around any problems you encounter. This just creates more complexity, which then requires more patches. Pretty soon the code is a mess. Yeah, but by this point, things are so bad that it will take months of work to clean it up. Yeah, it's exactly what we wrote just a moment ago, where it was. It was a subtle, yeah. Complexity makes harder to modify a system, effectively taking away how malleable this word's malleable, malleable. Oh, it's with an A, malleable, malleable. Okay, so yes, we were here. So effectively taking away how malleable it is. Yeah, it's exactly that. There is no way your schedule can tolerate that kind of delay, and fixing one or two of the problems doesn't seem like it will make much difference. So you just keep programming tactically, making the problem worse. So if you have worked on a large software project for very long, I suspect you have seen tactical programming at work and have experienced the problems that result. Okay. So once you start down the tactical path, it's difficult to change. Almost every software development organization has at least one developer who takes tactical programming to the extreme. A tactical tornado, tornado. The tactical tornado is a prolific programmer who pumps out code far faster than others but works in a totally tactical fashion. When it comes to implementing a quick feature, nobody gets it done faster than the tactical tornado. In some organizations, management treats tactical tornadoes as heroes. However, tactical tornadoes leave behind a wake of destruction. They are rarely considered heroes by the engineers who must work with their code in the future. Typically, other engineers must clean up the messes left behind by the tactical tornado, which makes it appear that those engineers, who are the real heroes, are making slower progress than the tactical tornado. Okay, we need to try to avoid to do this type of engineer programmer. Strategic programming. The first step towards becoming a good software designer is to realize that working code is not enough. Working code is not enough, guys. Remember this. It's not acceptable to introduce unnecessary complexities in order to finish your current task faster. The most important thing is the long term structure of the system. I mean, I agree, but still, there will be moments in which I guess it's necessary to do tactical programming. Just as long as those are very precise sections and this technical depth is fits quickly, I think it's okay. In my ignorance and in my perhaps lack of years of experience, this is what I think. But yeah, the word of this guy it's heavier than mine, so I will take it carefully. Let's say this statement, and I will remember this. So yeah, the approach is as we have to try to avoid tactical programming as much as possible, as much as possible. But still, I believe that there will be tiny moments in life in which tactical is needed. So let's continue. The most important thing is the long term. Yeah, most of the code in any system is written by extending the existing code base. So your most important job as a developer is to facilitate those future extensions. It makes sense, yeah. Thus, you should not think of working code as your primary goal, though of course your code must work. Your primary goal must be to produce a great design, which also happens to work. This is strategic programming. Strategic programming requires an investment mindset rather than taking the fastest path to finish your current project. You must invest time to improve the design of the system. These investments will slow you down a bit in the short term, but they will speed you up in the long term. Some of the investments will be proactive. For example, it's worth taking a little extra time to find a simple design for each new class rather than implementing the first idea that comes to mind. Okay, writing good documentation is another example of a proactive investment. Other investment will be reactive. No matter how much you invest up front, there will be inevitably be mistakes in your design decisions. When you discover a design problem, don't just ignore it or patch it around. Take a little extra time to fix it. If you program strategically, you will continually make small improvements to the system design. This is the opposite of tactical programming, where you are continually adding small bits of complexity that cause problems in the future. I'd like to add a statement. So, good software design or strategic programming is about investing and making yourself and making it easier. Let's leave it like that. It's about investing. How much to invest? So, what is the right amount of investment? A huge upfront investment, such as trying to design the entire system, won't be effective. This is the waterfall method. As we know, it doesn't work. The ideal design tends to emerge in bits and pieces as you get experience with the system. Thus, the best approach is to make lots of small investments on a continual basis. I suggest spending about 10, 20, Okay, this amount is small enough that it won't impact. Okay, okay. Yeah, got it. Yeah, this graph, it summarizes pretty good the idea. Okay, startups and investment. In some environments, there are strong forces working against a strategic approach. For example, early stage startups feel tremendous pressure to get. Okay, yeah, again, the settle note of one moment ago. You should realize that once a code base turns to spaghetti, it is nearly impossible to fix. You will probably pay high development costs for the life of the product. The payoff for good comes pretty quickly, so there is a good chance that the tactical approach won't even speed up your first product release. Another thing to consider is that one of the most important factors for success of a company is the quality of its engineers. The best way to lower development cost is to hire great engineers. However, the best engineers care deeply about good design. Facebook is an example of a startup that encouraged tactical programming. Okay, yeah, they did it wrongly. Then they has been spectacularly successful as a company. Over the time, the company realized that its culture was unsustainable. Yeah, that's the word for tactical programming. Let's let's put it as an insight now. Tactical programming is unsustainable. In fairness, so Google started with strategic approach from the go. Both companies, yeah, the company's strong technical cultures became well known in Silicon Valley. These examples show that a company can succeed with either approach. However, it's a lot more fun to work in a company that cares about software design and has a clean code base. Yeah, because you are less time fixing bugs caused by code of these tornado people. So you are spending more time like actually creating functionality and improving the system in general. So conclusion, good design doesn't come for free. It has to be something you invest in continually so that small problems don't accumulate into big ones. Fortunately, good design eventually pays for itself and sooner than you might think. It's crucial to be consistent in applying the strategic approach and to think of investment as something to do today, not tomorrow. When you get in a crunch, it will be tempting to put off claim ups until after the crunch is over. However, this is a slippery slope. After the current crunch, there will be almost certainly be another one and another after that. Once you start delaying design improvement, it's easy for the delays to become permanent and for your culture to slip into the tactical approach. The longer you wait to address design problems, the bigger they become. The solutions become more intimidating, which makes it easy to put them off even more. Yeah, it's what's the word? It's a vicious circle now. Vicious, vicious. No, you don't take the words for this. Violent and cruel. Now, oh yeah, it's a vicious spiral. Yeah, it's like that. This is a vicious spiral. Bigger it becomes, the solution become more intimidating, which makes it easy to put them off even more. The most effective approach is one where every engineer makes continuous, small investment in good design.